Welcome back to HoloBit. Today, we're going to model a tiny protocol economy powered by a bonding curve. Then we'll run experiments like a protocol designer to see how the system behaves. Here's the idea. On a bonding curve, price is a function of supply. When people buy and mint more tokens, supply goes up and the price moves up along the curve. When people sell and redeem, supply goes down and the price moves down. No order books, no market makers, just the curve. Price is discovered automatically from supply. We'll build this across 3 videos. In video 1, we build the core engine, including price calculation, token minting, and redeeming. In video 2, we add a DEX and arbitrage traders, and then watch market dynamics emerge. In video 3, we turn it into an experiment lab and tune parameters. So we build first, then we experiment. 2 quick notes before we start. 1, we focus on modeling, not math derivations. 2, if you've done the AMM case, feel free to speed through familiar parts. Ready? Let's build. We start with a minimum viable model containing 3 core parts, 1 game world, and 2 types of players. First, X protocol, the game world. It holds the rules, calculates prices, and executes transactions. It's passive and waits for users to interact. Second, team and investors. They enter first, mint during the presale, and kickstart the supply. Third, traders. They enter later, mint tokens during the public sale, and push the supply further. Now let's build, step by step. First, drag 3 agents onto the canvas and name them: X protocol, team and investors, and traders. For every agent, we always ask 2 questions. What is it? What can it do? Let's define what X protocol is first, using data components. For X protocol, the data falls into 3 categories. First, rule parameters. The curve settings that stay constant during a simulation, like maxSupply, price at 0 supply, and curveType. Second, state variables. The game state that changes in real time, such as the token pool, current supply, and current price. Third, helper variables. Tools for calculation and visualization. Let's start with rule parameters. Create 10 variables on the root canvas. These settings drive X protocol. We could put them inside the agent, but we keep them at the top level as global parameters for 2 reasons. First, they're easy to see and tweak before a run. Second, it avoids initialization order issues. Let's break them down by function. 4 of them control the curve shape: maxSupply, price at 0 supply, price at maxSupply, and curveType. 1 controls where the sigmoid curve bends, inflection point ratio. 3 control token allocation, presale ratio, public sale ratio, and initial liquidity ratio. 2 control fees, mint fee rate and redeem fee rate. For a default setup, set maxSupply to 100 million, price at 0 supply to 1, and price at maxSupply to 100. Set curveType to sigmoid, and set inflection point ratio to 0.5. Then, set presale ratio, public sale ratio, and initial liquidity ratio to 0.1 each. Set mint fee rate and redeem fee rate to 0 for now. You can also add controllers to adjust these later, just like we did in the AMM video. Now enter the X protocol canvas for state variables. First, drag in a container and name it issuancePool. It holds unminted X tokens and USDC reserves. For the container keys, we'll reuse the ERC20 tag set from the AMM case. Find ERC20 and push it into this model. Now add 1 more tag, X. Then back to the container panel, set ERC20 as the key, and enter the initial amounts for these 2 tokens, X to maxSupply, and USDC to 0. Both are non-negative. Then, create two more variables. Total X supply tracks how many tokens have been minted. Set its initial value to 0. Current X price shows the current price. Set initial value equal to price at 0 supply. For helper variables, create two more variables. One is curve points. Set it as a dictionary, and add two keys, supply and price. Then for their value, give them empty lists. This stores data that we collect to draw the curve. The other is calc step amount. Set its initial value to max supply divided by 10,000. This controls how finely we calculate transaction costs. Great! We've defined what X protocol is. Next, let's define what X protocol can do, its behaviors. In our minimal model, X protocol needs 6 processes in 2 categories. First, 2 processes for calculation: how to compute price from supply and how to draw the price curve. Second, 4 processes for transaction: how to mint tokens, how to redeem tokens, plus their helper calculations. Finally, go back to the root canvas and give X protocol a logo, like a Christmas tree. Set its color to purple, so it's easy to recognize. Next, let's define the other 2 participants. Now, team and investors. Set the type to population with an initial number of 10. They bring tokens into existence, push supply upward, and witness token price moving along the bonding curve. This agent is much simpler than X protocol. For data, drag in a container first and name it wallet. Use the same key, ERC20. This wallet stores their X and USDC tokens. Leave both amounts at the default 0. Allow negative for USDC, but keep X non-negative. Then, create 2 variables. Average pre-mint price, which records the average minting cost, the number investors care most about, and X holdings, which tracks total X tokens held by all individuals. Remember to change its belong to from individual to collective. For behavior, create one process, premintX. This mints tokens based on presale and initial liquidity ratios. The presale portion goes to early supporters. The liquidity portion stays in their wallet for now. In video 2, they'll deposit it into the DEX. Finally, give team and investors a logo, like an owl, and set it to green. Now let's define traders. We separate them from team and investors, because they enter the game at different times with different intentions, even though their minting action looks similar. The structure mirrors team and investors. So just copy team and investors, paste it on the same canvas, and rename the components. Rename wallet to trader wallet, and the 2 tracking variables to average buy price and trader X holdings. Rename the process to buy from public sales. Also, give traders a logo, like a sheep. Keep it green since it's the same agent type, but the icon makes it easy to tell them apart. So far, we've built the structure of our minimal model, which this time includes both the 3 agents and their variables. Next, let's make them actually do things. We'll start by configuring X protocol's process, calculating price from supply. First, set up its ports. 1 input port, input supply, the supply amount to calculate. 1 output port, output price, the calculated price at that supply level. Next, for the calculation logic, we need a gateway to check the curveType, then branch into 4 calculation paths. On each branch, insert a compute component, then connect them all to an end event. All components are in place. Now let's configure them one by one. Set the gateway as conditional. Add 4 conditions based on curveType: linear, power, exponential, and sigmoid. Each condition leads to its corresponding compute. For each compute, we enter the corresponding formula. Linear is straightforward. Price increases in a straight line from initial to max. Power uses logarithmic growth. Exponential creates a steeper curve. Sigmoid creates an S-curve with an inflection point. The exact formulas are on screen. You can also find them in the model file. One important setting: open advanced settings and set concurrency limit to 0. This process computes a result without modifying any shared data. So it's safe to allow unlimited parallel queries. The price calculator is ready. Now let's draw the price curve. This process runs once at startup. It scans the entire supply range and collects data points. We plan to collect 101 data points, enough to draw a smooth curve. Here's a powerful technique: loops. Instead of building 101 separate calculations, we create one loop that repeats automatically. Every loop has 3 elements: the task to repeat, a counter to track progress, and an exit condition. Let's build it in that order. First, the task. Insert a call component to execute the calculation. Second, the counter. Create a process variable named I with initial value 0. Third, the exit condition. Add a gateway. If variable I exceeds maxSupply, exit and go to the end. Otherwise, continue to repeat the task. Draw a link from the gateway back to the call. Loop complete. Let's configure them in detail. First, keep the start event as normal and turn the active switch on. This process will draw the blueprint of supply and price at the start. Then, configure the call. It calls self's calcPriceFromSupply. Pass variable I to the input supply port. Before each call, record the supply data. In compute before action, append variable I to curvePoints.supply. After each call, record the price and update the counter. In compute after action, append the output price to curvePoints.price. Then add maxSupply divided by 100 to variable I. Here's a pro tip: always set initial value for process variables. If you skip this, variable I defaults to null, and you'll get an error saying cannot perform operation on number and null. Next, set the gateway to conditional and add the condition. If variable I is greater than maxSupply, go to end. Otherwise, go back to call. That completes the loop. Let's test it. Go to the root canvas. Switch curve points to monitor mode, and create one chart based on it. Run the model. You can see it. The curve points dictionary is filling with data, but the chart doesn't show the S-curve yet. Here's why. Charts default to history mode, which tracks how values change over time. But curve points isn't a time series. It's a data structure with supply and price lists. So, switch from history to latest. Then set the x-axis to supply and y-axis to price. There it is, a beautiful sigmoid curve. You can also try switching curve types, like power and exponential. Each curve shapes price differently. Then switch back to sigmoid for the rest of this tutorial. Great! Our first milestone is complete. X protocol now knows how to calculate prices and draw the blueprint. Next, let's build the transaction behaviors. Mint and redeem. We'll start with mint. A mint is just an exchange between X and USDC. The key question is, when you mint X, how much USDC do you pay? It's not just price times quantity. On a bonding curve, each small purchase pushes the price higher. The true cost is the sum of all those tiny increases, the area under the curve. So, we break one large transaction into many small steps, loop through them, and add up the cost. Now let's begin with calcMintX. First, set up its ports. Add one input port. Target amount. This receives how much X the user wants to mint. Add 4 output ports: actual amount, total cost, effective price, and next price. Set total cost's default value to 0. This avoids errors when the value is null. Now build the process flow. First, we check if there's any X left to mint. Add a gateway after the start. One branch ends the process if no X remains. The other branch continues. For the continuing branch, we'll use a loop again, but this one is more complex. First, the task. Insert a call to run the price calculation. Second, the counter. Create a process variable called amountProcessed with initial value 0. Also create a helper variable called stepAmount. This is how much X we mint in each loop. It equals calc stepAmount most of the time, but it shrinks to fit when the remaining amount is smaller, either because the total demand is small or it's the last step. Third, the exit condition. Add a gateway with 2 branches. One exits the loop, one continues. For the continuing branch, connect a sequence connector back to the call to form the loop. After the loop, we need one more price calculation to get the next price at the final supply. Insert another call before the end. That's the full process. Now let's configure each component. For the start event, keep the default settings. Normal type, active off. This process waits for users to call it. For the first gateway, set it to conditional. Add the condition. If the remaining X in issuance pool is less than or equal to 0, end the process. Otherwise, continue. In its compute after action, use this formula to confirm actual amount. This prevents minting more than what's available. Now configure the loop call. Leave owner as self, and set the behavior to calcPriceFromSupply. For input supply, use the expression here. It calculates the current supply plus the amount already processed. In compute before action, use the formula. This ensures step amount never exceeds the remaining amount. In compute after action, add 2 lines. The first one updates the counter, the second one accumulates the cost. For the exit gateway, set it to conditional. Add the condition. If true, exit the loop. Otherwise, continue. For the final call, set it to call self's calcPriceFromSupply. Pass the final supply value to the input port. In compute before action, use the formula to calculate the average price. In compute after action, enter the formula to update the new price. Great, calcMintX is done. Next, let's build mintX, the actual minting process. mintX does 2 things. It tells the user the required input amount, and it performs the token transfer. First, set up its ports. Add 3 variable ports as inputs: amount out, input token, and output token. And 1 container port, user wallet. Amount out is numeric. Input token and output token are strings. User wallet is a container port. Add 2 output ports, amount in and effective price. Now think through the logic. mintX calls the calculation to get the cost, then uses container operate to transfer tokens and an end event to close the process. Now configure each component. For the start event, keep the default settings. For the call, set it to call self's calcMintX. Pass amount out to the target amount port. In compute after action, add 2 formulas to get amount in and effective price. For the container operate component, first drag in references for issuancePool and the user wallet port. Connect them to the container operate component in order. This automatically turns on the exchange switch. Then set up 2 transfer directions. First direction, the connector from user wallet to container operate, key set as input token, the amount set as amount in. And from container operate to issuancePool, same key and auto amount. Second direction, the connector from issuancePool to container operate. Key set as output token, the amount set as amount out. And from container operate to user wallet, same key and auto amount. Finally, in compute after action, add the formulas to update the protocol states. mintX is done. Now let's wire up the user agents. First, team and investors pre-mintX process. This is an active behavior. Turn on active. Insert a call component followed by an end event. For the start, keep normal type. They finish this at the start. For the call, set owner to X protocol. Set behavior to mintX. For amount out, enter this expression. It calculates each individual's share of pre-sale and initial liquidity tokens. Set input token to USDC. Set output token to X. Create the wallet reference and connect it to the user wallet port. In compute after action, add the formula to calculate the average price during the pre-minting. Next, traders buy from public sale process. The logic is similar to premintX. Copy the process and paste it on the trader canvas. Then adapt it. Change the start event to timer, starting from tick 2, with a total time of 1. This ensures the public sale happens after the pre-minting. For the call, keep the same settings, but change the amount. For amount out, enter the formula for the public sale portion. For user wallet, the copied reference is now empty because the scope changed. Set it to trader wallet. In compute after action, add the formula to calculate the average price during the public sale. Now let's test the model. Go back to the root canvas. Switch key containers and variables to monitor mode and give them a clear layout. Create a chart for current X price. Change its type to scatter and set its x-axis to total X supply. Click step once to check the initial data. IssuancePool shows 100 million X, the max supply we set. Then hit Resume to run. Let's verify the results. First, the price supply curve still looks sigmoid. Second, IssuancePool X decreased by 30 million. Total X supply is 30 million. Each of the 10 team and investor individuals gained 2 million X. Each of the 10 trader individuals gained 1 million X. The X changes are correct. Third, the current X price chart shows 2 values, since we only ran 2 ticks. At 30 million supply, price is about 14. This matches the price supply curve. Finally, average premint price shows each individual has a different cost, all lower than current price, trending upward. As supply increases, price rises. This matches the curve logic. The data confirms our model is working. You can also try different parameters. For example, switch curveType to linear, reset and run again. The results show how curve shape affects the system. You'll find current price jumps significantly higher than under sigmoid. The average minting cost is also much higher. This explains why linear curves are less common. S-curves give early participants better prices, making it easier to bootstrap a protocol. After testing, switch back to sigmoid. Great, we've now completed the minting processes. Now let's handle redemption. The logic is almost identical, just reversed. So instead of building from scratch, we'll copy the minting processes, rename the components, and make a few adjustments. Here are the key changes. For calcRedeemUSDC, rename the output port total cost to redeem value. Keep its default at 0. For the first gateway, change the condition. If IssuancePool X is greater than or equal to maxSupply, end the process. This means there's nothing to redeem yet. In the loop call, update the input supply formula. Instead of adding amount processed, subtract it. In compute after action, update redeem value instead of total cost. For the final call, apply the same logic to input supply. Subtract actual amount instead of adding it. In compute before action, update the formula for effective price to use redeem value. For redeemUSDC, swap the directions. Amount in becomes an input port. Amount out becomes an output port. During redemption, users know how much X they have. They want to find out how much USDC they get back. Update the call to match. Pass amount into the target amount port. In compute after action, set amount out to this redeem value. For the container operate component, update compute after action. Set current X price to calcRedeemNextPrice. That's it for redemption. We've now built a complete minimum model. We tested minting with team and investors, then with traders. The core math logic works. The protocol's cold start is complete. In the next video, we'll add more participants and watch the dynamics unfold.